So next up we have Rasmus Møgelberg from at the University of Copenhagen, who's going to tell us more about probabilistic programming in guarded type theory.
Is this working? Microphone? Okay. The slides are not working. Okay. Probabilistic programming is everywhere, also here at POPL. And there are good reasons for that. It's because it's used in important applications like machine learning and statistical modeling, and also in security. Now, we'd like to be able not just to program probabilistic programs, but also reason about them. And that's particularly challenging when the programming language has other features, such as recursion and higher order functions. So let me start with a few toy examples of the kind of reasoning that we'd like to be able to do. And so here's the hesitant identity function. The hesitant identity function takes an x as input, and with probability p, it returns the x. Probability 1 minus p, it calls itself recursively. Now, this hesitant identity function, with probability 1, it will eventually return its input. So it should be contextually equivalent to the identity function. And indeed, we prove that using the methods here in this paper. Here's another small example. It's an encoding of a fair coin using a bias coin. If you have a bias coin, you can encode a fair coin by flipping the bias coin twice. If you get different results, you pick the first result. If you get the same result, then you try again. So this is a recursive program here. And we prove in this paper also that, that this encoding is indeed an encoding of a fair coin. It's equivalent, contextually equivalent to a fair choice between true and false. In the paper, we also have some reasoning about Markov chains. Now, there has been a lot of work in this area, and indeed, all these examples that I show here, they have been proved in other settings, in using other tools. But the challenge here is that modeling this combination is quite challenging, and so the existing models are all quite complicated. And so what we'd like to do is we'd like to develop a simple model of this combination of features. And the way we do that is that we express this model in a powerful meta-language. And the meta-language you use is clock cubical type theory. It's a type theory that has guarded recursion in it. And we use guarded recursion for modeling recursion in the object language, for constructing relations between syntax and semantics, and for reasoning about programs. And in particular, we introduce the guarded convex delay monad as a way of modeling this combination of probabilistic choice and recursion. And so you may say that what we're doing is that we're delegating the difficulties in modeling, in particular recursion, to the model of the meta-language. So let's look a bit closer at what we do. So probabilistic computation by itself can be modeled using the finite distribution monad. And here I have the classical presentation of the finite distribution monad. And this would be used both for constructing operational and denotational semantics of these languages. Now, recursion is generally harder to model. It's usually not just a monad. Instead, the standard model of recursion is domain theory, and that requires a complete change of the setup. Or you could use step indexing, and that's also quite complicated. So it turns out that there is actually a monad for recursion. It's this delay monad, and it's a co-inductive solution to this type equation I have here. So it says that a computation in this delay monad is either a value of type A, or it's a computation that can run for at least one more step. And it's co-inductive, so you can be infinitely often on the right-hand side here, and that corresponds to divergence. And this monad is actually used to model recursion in type theory. It's also used in interaction trees. And we can easily combine, extend this to also model probabilistic choice in what I'll call the convex delay monad, which is the co-inductive solution to this equation down here. Okay, so this one says now that a computation now is not either a value or computation that can run for one more step, but a distribution of such things. And so this is actually a very natural model of this combination of recursion and probabilistic choice. So for instance, if we're modeling the geometric process here, which given an n returns n with probability p, probability 1 minus p calls itself recursively by n+1. We can model that in this monad as a tree like this, where the branching here is a distribution. And so the idea is that we want to represent terms of the programming language as these kind of trees, because once we have represented a closed term, at least, as a tree like this, then we can start doing basic operations on them. So for instance, we can run such a tree for one step, so eliminating one level of steps here like this. Or we can run it one step more, and it looks like this. Okay? And then after 2 steps, I can measure the probability of termination after 2 steps by just summing up the probabilities of the values, in this case 0, 1, and 2. Okay? And then I can define sort of a limit process, and the limit of this thing here is then the probability of termination of the whole process. Okay. So that's all good and nice, but there's one problem here with this convex delay monad, and it is that it's not really a model of recursion, at least not for higher order languages. So it models an iteration operation of this type here, but there's no general fixed point operation of this type down here. Okay, and this is a problem when you're modeling higher order languages. And so this is the place where we step to a guided recursion. So we replaced the convex delay monad that I showed you before with a guided convex delay monad. And it's the same, it satisfies the same type equation as we saw before, except that the computations now are delayed by this model operator later on clock kappa. Okay, so we're no longer just in ordinary set theory, in ordinary type theory. Now we're in a type theory that has guarded recursion. And it means that we have this model operator, and we have an operation next which transports data into the future. So later x classifies data of type x, that's delayed by one time step. So next transports data into the future, and we have a fixed point operation like this, and a Carnot-style fixed point. And that fixed point operation is very powerful. As a small example, you can encode, for instance, diverging computation as an element of this monad here. And so the benefit of this monad here, the guarded convex delay monad, is that it does actually have a fixed point operation of this type here. So we can use it to model also higher order languages with this combination of recursion and probabilistic choice. And moreover, we can pass through the co-inductive monad, the ordinary delay monad that I showed you before, by simply quantifying over the clock kappa used in the definition of this guarded convex delay monad. Okay, and this gives us a way of having the best of both worlds, of the co-inductive and the guarded world. So in the paper, and a few more details, in the paper we work, as I said, in clock cubical type theory. It's a type theory with guarded recursion. One way to view this is through its pre-sheaf semantics. And the pre-sheaf semantics captures, in a way, the essence of the step index model. So you can think of this as an abstract language for step indexing. But you can also work directly with it in an extension of cubical acta, although we haven't used it for this particular application. So what we do in the paper is that we model a language called probabilistic FBC, construct operational and denotational models. We prove an adequacy theorem, and then we use that adequacy theorem to do examples of reasoning. So let me show you a few more details of this. Here's the probabilistic FBC. It's the simply typed lambda calculus extended with recursive types. You have the fold and unfold, and then probabilistic choice. And so we define an operational semantics. And the operational semantics is just given by an evaluation function that takes a term of type sigma and returns a value of type sigma. Of course, that computation uses recursion and it uses probabilistic choice, but we can model that using this monad here. And so, for instance, if we're to evaluate an application, well, you evaluate m to a value, which is necessarily a lambda. Then you evaluate n to another value, and then we substitute the value into the body of the lambda and keep evaluating. And of course, we can't define this by induction or recursion on terms. So what we do instead is we take a step, as you can see with the next here, and that takes us under later, and it means that we can define this evaluation function by guarded recursion using the fixed point operation I showed you before. We can then pass through the co-inductive evaluation by simply quantifying over the clock. And this means that we can define, for instance, contextual equivalence like this, essentially the standard way. So you take, you say m smaller than n in this relation here for any context. When I put these terms in the same context and I evaluate, then measure the probability of termination, then the probability of termination on the left-hand side is smaller than on the right-hand side. The denotational semantics is even simpler. So it's essentially modulus corpora value semantics, monadic corpora value semantics, as we can see from the function space over there that uses the monad, the guarded convex delay monad. And then recursive types are modeled using guarded recursive types, which exist in this meta-language. So here, interpretation of terms for a function application is just monadic bind. We then construct a logical relation. In fact, we construct two logical relations, one between semantic values and syntactic values, and another one between semantic terms and syntactic terms. And in fact, the second one of these is obtained from the first one by a lifting operation, which is one of the main technical contributions of the paper. So the lifting operation uses couplings, but I don't want to go into details of that. The value relation is defined also by guarded recursion. For example, in the case of the recursive type over here, we're going on that later, and that's how we define it by guarded recursion. And so we prove the main theorem here, which says that if the denotation of m is smaller than the evaluation of n in this relation here, then m and n are related in this contextual equivalence, contextual approximation relation. And so we can use this main theorem here to prove to reason about programs. And I'll just do a small example of this. Here's the hesitant identity function. Takes an x, returns x with probability p, probability 1 minus p, it calls itself recursively. And we'd like to show that that's equivalent to the identity function. And I'll just sketch one way of this proof here. So in order to show that the hesitant identity is related to the identity, it suffices by the main theorem to show that the denotational semantics of the hesitant identity is related to the identity function. And because this is a logical relation, in order to prove that, we just need to show that they map related inputs to related outputs. So suppose we're given two related inputs, small v and capital V. We need to prove one here which says that the results of applying these are also related. And so how do we do that? Well, we unfold the definition of the denotational semantics of the hesitant identity. And that unfolds the recursive definition of the hesitant identity and adds a step. And because it adds a step here, by definition, this one here would be equivalent to a relation of the unfolded things, but later. And that means that we can prove this one here by guarded recursion. Okay? So by that I mean, to prove one, it suffices to prove one, assuming that later one holds. And if we assume later one holds, then we can prove two, because that's a statement under later. So if we assume later one holds, then two holds, and two was equivalent to one, and the proof is done. Okay, in conclusion, we saw that we could use cubical type theory, which is a type theory for guarded recursion. We use that as a meta-language for doing semantics of probabilistic FPC. We used guarded recursion both in the definition of the operational and denotational semantics, and also in constructing this relation here. And I believe that this is perhaps the simplest possible construction you could do of this. What we're doing, as I said, essentially is we're delegating the difficulties in modeling recursion to the modeling of the meta-language. Okay, thank you.
Thank you, Rasmus. Any questions?
So you use guarded recursion to define the operational semantics. How much work would it be to show that definition of the operational semantics is kind of equivalent to a more naive thing that's just defining it in terms of iteration and limiting the number of unrollings of the loops?
So we looked at various different definitions of operational semantics. I think there are different ways of constructing operational semantics for probabilistic languages. So I would expect it to be relatively straightforward to prove that for some of these, but we haven't done it.
And can I do that proof kind of internally in the type theory?
Yes, absolutely, yes, yeah. Well, we haven't done it, but I would be very surprised if you couldn't, yes.
I have not really understood what the type.
Sorry?
What is the guarantee that is provided by typeable expression relative to their semantics? I have not understood that.
The guarantee that what, sorry?
When you have a program which is typeable, the fact that
yes,
type system.
Well, we guarantee that the definition of the operational and denotational semantics is well defined. I think that's all.
But that's undecidable.
Well, I mean, so what do type systems do? I mean, they guarantee that programs don't go wrong at runtime, you might say. Right? So that's.
And what does it mean, go wrong?
Well, it means they're applying something that's not a function to an input, for instance.
So, for example, you have no probabilistic guarantees?
Not just from typing, no. I mean, so the idea is that you can write whatever language you like, and then you can reason about it afterwards, using these tools that I showed here. So you prove it afterwards.
Okay. I don't see the real progress, but maybe I'm the only one.
Questions? Right here.
Thanks for the talk. This might be a naive question, but is there semantics of the meta language? And if you sort of were to unfold going through like your encoding and then the semantics of the meta language, do you have a sense of how this relates to other approaches of giving semantics to FPC, probabilistic FPC?
So you would get a step index model, because the semantics is a presheet model, which, as I said, encapsulates sort of the step index models, yes. So I think you could do that, yeah.
Any final questions? All right, let's thank Rasmus then.